unserem nächsten Talk Energiespeicher von heute für die Energie von morgen mit Sebastian.
Welcome to our next talk, Energy Storage of Today for the Energy of Tomorrow.
Erneuerbare Energien sind der heiße Scheiß.
Short version is renewable energy are really hot shit, but what do we still have to research? What can we do? What can't we do yet? And our speaker, who has been here at Congress for 10 years, will tell us about this. And it's informed by his tendency to open up and take apart anything and everything. And this talk will be about various ways of storing energy, mainly batteries, and what actually goes on inside them. So have fun with Sebastian, and applause please.
Ja, herzlich willkommen.
Okay, welcome to my talk. It's very full, I wouldn't have thought that.
Okay.
Okay.
Ja, Energiespeicher von heute.
Energy storage of today.
Mir ist durch meine Twitter-Timeline gerollt, immer wieder Artikel.
In my Twitter timeline I tend to find news articles about what's better, a battery-powered car, a fuel cell-powered car, one of both.
Und dann habe ich mir das angesehen und dachte mir,
And I had a look at all that and thought,
erzählen eine Menge Leute sehr halbgares Zeug.
a lot of people
Und es
are
werden
talking
Aspekte rausgegriffen,
not
eine
very
bestimmte
good
Technologie besonders
stuff.
gut aussehen lassen, aber eigentlich
They're picking aspects
beide gar
that
nicht so
favor
richtig
one
miteinander
technology
vergleichbar
over the
Als
other,
Bild würde ich
but they're not
schlagen
really
vor,
comparable.
Wenn man einen Pinguin in die Wüste setzt,
To paint an
dann
image,
sieht der da nicht
if you
sonderlich
put a
gut aus.
penguin into the desert,
Wenn man ein Kamel
it
damit
doesn't do
vergleicht,
that well. If you
das
compare it to
Kamel
a
deutlich schneller.
camel, the camel is
Wenn
much
ihr beide
faster.
zusammen ins Meer packt,
If you take both and throw them into the sea,
sieht viel besser aus.
the penguin's doing well.
Und da das alles ein bisschen
And,
genauer hinzugucken ist, dachte
well,
ich mir, vielleicht
You
kann man
just
die
have to
Theorie ein
look
bisschen
closer at things, so I thought, why not tell you all
Und
about it?
zwar, war ich eigentlich einen
So,
ganz guten
why?
Überblick über die ganze Geschichte
Because
haben.
I
Ich
seem
habe
to kind of
Chemie
know what I'm
studiert,
doing.
ganz klassisch auf Diplom.
I studied
Habe
chemistry,
angefangen,
got
mit
my
organischer Chemie,
PhD.
Biochemie,
I started
und
with
habe dann im
organic
Verlauf des
and
Studiums festgestellt,
electrochemistry,
naja, da ist die
and
Labor-
during my
nicht
studies
ganz so mein
I
Ding.
sort of saw, yeah, no,
Und, bin dann
labs,
auf,
nah, not my
erst
thing.
auf Brennstoffzellen und
And then I
Wasserstofftechnologie
switched
aufmerksam
to
geworden.
fuel
Dann
cell
hatte
and
ich einen
hydrogen technology,
studentischer Hilfskraftjob am Fraunhofer-Institut für Zuverlässigkeit und Mikrointegration.
worked for the
Wo es
university
tatsächlich
for
darum
money,
ging, Lithium-Ionen-Batterien
and
auf
my
kleiner
job
Skala
was to
aufzubauen und,
build
die
small-scale
potenziell in eine Platine
lithium batteries,
zu integrieren. Also quasi das,
so
was
small
man
that you can
ein paar
actually
Euro aus China
integrate them
liefern
into a
kann,
circuit
eine
board.
kleine Vertiefung reingefräst,
You know, just
Batterie
order a cheap
eingebaut,
circuit board
Deckel
from
drauf, und dann
China,
halt eingebaut
mill a
eine
small hole in it,
Batterie. Nicht mehr so wie
put the
üblich
battery in
vermittelt.
there, and now you have an integrated battery,
Genau,
not
und,
soldered
meinen
to
Abschluss
the edge of
habe
the
ich
board
gemacht
somewhere.
am Helmholtz-Zentrum Berlin.
And I actually did my
Da in der
PhD at the
Mitte
Helmholtz
in der
Zentrum
Stadt
in
ist die
Berlin.
Technische Universität.
In the middle you can
Und das
see the
Helmholtz-Zentrum hat
Technical
zwei
University,
Standorte, einmal unten
and the
rechts
Helmholtz Zentrum
Adlershof
has two sites,
und unten links in
bottom
Wannsee.
right Aldershof, bottom
Und
left
stehen jeweils
Wannsee.
zwei Großgeräte.
And they have
Einmal
two
der
very big
BR-Fach-
devices. The
beziehungsweise
BR
aber er wurde
research
jetzt
reactor,
kürzlich
which
abgeschaltet
has
nach
been switched
3
off
Jahren Vorlauf,
recently.
und guter Vorbereitung ist jetzt vor kurzem der Abschluss gefeiert worden.
We prepared for it
Und, der
and
Reaktor wird
we
jetzt in den nächsten
turned it
Jahren
off,
langsam
and in the next few
runtergefahren.
years
An
it'll
dem
be
Standort habe ich meine Forschung betrieben. Und an der
run
anderen
until
Stelle
it's
ist
cooled down.
zwei Synchrotronen,
On the other
wo
place
dann,
there's the
eine Menge
Bessie 2
Material
synchrotron,
gemacht werden,
where they do a
auch,
lot of material
Anwendungen
science
zu Solarenergie,
and a lot of
hauptsächlich
stuff about
bekannt
solar
zum
energy,
Solarzellen oder
mostly
auch,
silicon
Perovskit
photovoltaics,
Solarzellen
but also
geforscht werden und
perovskite.
die Materialeigenschaften und
And
Struktur
they
untersucht wird.
characterize the materials and the structures there.
Zuerst, wenn es um einen Energiespeicher geht,
First of
braucht
all,
man
when
zwei
we're
Dinge.
talking energy storage, you
Material
need two
und Platz
things:
dafür.
materials and a place to put them.
Energiedichte bildet sozusagen ab,
The energy
einmal
density
auf der Hochachse
has on the vertical axis the
Wattstunden pro
specific
Kilogramm,
energy
das ist dann
in
auch die
watt hours
Masse
per kilogram,
dazu. Da ist
so
dann klar,
energy
man
per
sieht
mass,
eine Bleibatterie, die normalen
which
Batterien
shows
sind relativ schwer.
lead batteries,
Und
normal
jetzt
batteries
zum
are
Beispiel,
relatively heavy.
Kondensatoren kennt man auch
At the
von
bottom you
aus
see
kleiner Skala, was man
capacitors.
so auf Platinen drauflötet.
You know them
Leicht.
from circuit boards, they're light,
Und auf der Achse quer ist die
and on the horizontal axis
Kilogramm
we have the power
Das
per
heißt,
kilogram.
wie
which means how fast can I dump the energy out of
Das
there.
heißt, Metalloxidkapazität,
So,
Capacitors,
metal oxide
oder
capacitors,
auch die sogenannten
or
Supercaps,
so-called
sind
supercaps.
die auch
That's a
teilweise
key
im
word for this,
Kontext Elektromobilität,
at least in this context
zum
of
Tragen kommen.
electromobility.
Die sind sehr schnell entladbar.
They're
Allerdings sind das keine
dischargeable
chemischen,
really
sondern
fast,
eigentlich mehr
but
physikalische
they're technically not
Energiespeicher.
chemical energy storage,
Und
but
was
physical.
mich jetzt besonders interessiert,
And
oder was
what
mein
interests
Fachgebiet
me
eher ist, sind eben
personally
Batterien und da oben
is batteries
tatsächlich chemische Energieträger,
and
also das, was wir
chemical
kennen,
energy
das ist
storage.
Benzin oder auch Wasserstoff.
So gasoline,
Und
hydrogen.
dann schauen wir uns mal ein Diagramm an.
And we
Jetzt
can
mal
look
etwas
at
aus der Nähe.
this diagram.
Hier ist mir die Achsbeschriftung flöten gegangen.
And
hier ist die Beschriftung
my
ein bisschen
axis
anders. Hier geht es jetzt
information just
die
vanished.
Energieinhalt aufs Volumen bezogen.
And this is the
und
energy
Energieinhalt aufs
density
Gewicht bezogen.
per volume compared to the
Volumen
energy
ist die
density
Achse
per
quer.
mass. Volume is the horizontal axis.
Oder? Ja,
Yes,
habe ich
correct.
im Studium gelernt.
I learned that in my
Das
studies.
heißt, man muss seine Achsen beschriften, sonst passiert
I
sowas.
learned in my studies that you have to label your axes or this sort of thing happens.
Also die Hochachse ist
So
die
the
Volumetrische,
vertical
also auf
axis
Volumen
is the
bezogene
axis
Achse.
for the volume,
Das sieht man daran, unten
and you
die
see this
Methan,
on the
Wasserstoff sind
bottom. There
gasförmig.
is
Das heißt, man kriegt von
methane
dem
and
großen Volumen
hydrogen.
nur relativ
So it
wenig
means
Energie
that you
gespeichert.
need a
Das
big
sieht dann anders aus, wenn man
volume
die
for
Linie
less
mal nach oben
energy.
geht.
And if you
Sieht man
follow
da
the line to the
Erdgas
top,
200 Bar, das ist,
you
was
see
wir
there
alle
is
als LPG-Gas auch von der,
fossil
von
gas,
der Tankstelle
and
erkennen.
this is
Zum
what you
Beispiel.
know from the
Oder dann eben
gas
entsprechend
station.
darüber Wasserstoff flüssig, Wasserstoff
Above them there is
hochkomprimiert,
hydrogen
Wasserstoff und
in a
dann
liquid
ganz
form,
oben
and
die,
on the very, very top
üblichen,
you see that there is
Treibstoffe,
the
Ethanol, Benzin, Diesel, oben
usual
sogar auch,
usual
von Metall
suspects like
aufgeführt. Graphit
benzylene and
ist auch quasi ein
graphite,
Kohlenstoff.
like so
Aluminium kann man auch
basically
verbrennen
carbon.
potenziell.
You also could burn aluminium, which
Wer
has
hat
a very
mal
high
einen
energy.
Feuerlöscher in der Hand gehabt, wo ABC
If
draufsteht?
you had,
Mal
who
Hand heben.
who of you has been working
Ja,
with
so
an
ziemlich jeder.
fire
Wer hat
extinguisher
einen in der Hand
with
gehabt, wo Klasse D
ABC?
draufsteht?
Has some of you
Ja,
even had a
ungefähr so
class
10,
D one?
15 Hände.
So it's above about 10
Die
hands here.
Feuerlöscher der Klasse D sind spezifisch für Metallbrände,
Fire
weil
extinguisher
Metall tatsächlich
of the
so
class
heiß
D
und, relativ schwer zu löschen sind, dass man
are
dafür
especially
spezielle
for
Löschmaterialien braucht.
metal burnings because they are very hard to extinguish. You see this, but they are really on top of this diagram. And you see here where I tried with the mouse, but it's not showing up. That's a pity.
Und links in der Ecke sieht man
In
dann
the
Gleichsäureanode.
bottom
Das
left,
ist eben
you
die
see
bekannte
that there is
Autobatterie.
a LED
Ist ziemlich weit
LED
hinten, weil
battery.
ist für
This
die
is very low in
Energiespeicher
this
ziemlich
diagram
schwer.
because it's very heavy
Darüber
in,
kommen dann die anderen
in
Batterien.
with regards to the energy it's storing.
NIMH ist so, das,
And,
was man heutzutage üblich so in Fernbedienungen
Then
oder
you have the
beispielsweise dieses
usual
React-Badge reinsteckt.
NEMH batteries, which you find in your probably DECT phone. The alkali batteries, which are not rechargeable, and then slightly below that the lithium-ion batteries, which recently got the Nobel Prize. So again, here the question: who has got a device with a lithium-ion battery? Okay. So basically everyone. 2, 3, 5, 20. Okay, now the hands are getting less, but basically everyone has them. The technology is everywhere. So what means lithium ion? Lithium is an alkali metal, so the third metal in the period system. It has 3 electrons, and if you remove one of the electrons from the atom, you get an ion, which means that it's a positively charged lithium core. And this is actually storing the charge in the battery. These are the 3 people who got the Nobel Prize for the lithium-ion batteries. The John B. Goodenough.
Es wird gerätselt, ob sich seine Eltern dabei mit einem Augenzwinkern
there's a question if the parents had a twinkling eye with the bee.
Und
and Stanley Whitingham, Akira Yoshimo, and the Nobel Prize Committee has very nice documents on the topic, which I will now explain.
Das ist erstmal die erste Iteration.
This was the first iteration,
wo noch an der Anode tatsächlich ein Block Lithium-Metall
where there was actually a block of metallic lithium for the anode. Which one of you had chemistry in school?
Leistungskurs?
Good chemistry?
Das ist dünn.
Oh, that's getting thin.
Wer hat mal ein Stückchen Natrium in Wasser geschmissen?
Which one of you has thrown sodium into water? Ah, more than half.
Das spritzelt und brennt und explodiert.
It burns and sooner or later explodes. So all alkaline metals react that way with water, which means it's a bit of a problem to put a whole block of them into a battery like that. Which is the reason why you shouldn't open these batteries, because even the moisture in the air can be enough for the metal to react with the metal in there. And yeah, then it's gonna get warm and colorful.
So, zurück zu der Batterie selber.
So back to the battery
Das heißt,
itself.
wir haben an der Anode
At the anode we have
das Lithiummetall
the
gibt
lithium
sein
metal,
Elektron ab.
and that lithium metal
Wird durch das elektrische
gives
Feld
off
beim Aufladen
an electron,
gezwungen, überredet.
or rather it is forced to do so
Wenn die Batterie
while
aufgeladen
charging.
ist, fließt das
When the
Elektron
battery
durch
is
den Verbraucher
charged,
auf
the
die andere Seite
electron
zurück
flows through the
und
load
wird in
back to
dieser
the other
Iteration
side,
in einem Material
and
Titan
in this
disulfid
iteration is
Titan ist
stored
ein
in
Metall,
titanium disulfide.
relativ bekannt
Titanium is a
eigentlich.
metal too,
Weiße
fairly well
Wandfarbe kennt
known.
auch jeder,
You know,
Titandioxid.
that white paint for walls, titanium dioxide is a very well known and cheap pigment. Here it's the sulfur analog disulfide, and here at the battery we can see 2 volts of cell voltage. That's more than a normal battery with 1.5, but the problem was this thing chemically self-destructs over time. Next iteration, cobalt oxide.
Das war jetzt stabil.
This is stable,
Diese Batterie war halt nicht nach 2-3 Mal aufladen und entladen.
and the battery isn't dead after 2 or 3 charge or discharge cycles. The cell voltage was a bit higher. We still have the lithium metal on the anode side,
Und am Schluss kam dann
and at the end
die Innovation, okay,
we had the innovation
Metall
of
loswerden möchte.
getting rid of that metal block. The question was how to
Und da
do
hat
that,
Yoshino
and
rausgefunden,
Yoshino
hey,
found out that,
Graphit,
hey,
also
we
quasi
can
das, woraus man
use
Bleistiftmine
graphite for the
Graphit
stuff
hat
you
so
make
eine,
pencils from,
Wabenstruktur,
and it has this hexagonal structure, kind of
das sind
like
Schichten, die in
beeswax.
parallel übereinander aufgeschichtet sind. Und
And
dazwischen
those structures are layered one above the other, and there's some room between them.
Lithium-Ionen gut dazwischen.
And you can shove lithium ions
Tatsächlich
between
da
those layers.
Zahl 3, es ist wirklich sozusagen fast das kleinste Atom, was man sich denken
Lithium,
kann. Dementsprechend
with
ist auch
the
noch
atomic
krass.
number of 3, is one of
Und das
the
kann man
smallest
eben
elements you
in
can think of, so it doesn't need
Graphit
much
oder hier
room.
Petrol,
So you can store it in graphite, or here petroleum coke.
Koks quasi. Also nicht das zum Schnüffeln,
So,
sondern das zum Verbrennen.
Not the coke for your
Kann man
nose,
das
but the one for
einlagern und hat
burning.
plötzlich nicht mehr diesen hochreaktiven
You can
Metallblock
store it in
da.
there, and you
Oder
don't
halt
have
nicht,
this
sondern
highly reactive
was
metal
besser
block or layer
handhabbares.
anymore, but something that can be handled much more
Hat sich
easier.
dann dazu entwickelt, was wir heutzutage
And
in
the
allen
combination has
Systemen drin haben.
developed into things, into what we have in every device now.
Was nicht so mein Fachgebiet ist, aber was natürlich auch diskutiert werden muss, ist, woher kriegt man diese Materialien eigentlich? Kobaltoxid insbesondere.
What's not my
ist,
field of expertise, but has to be discussed, is where do you get that stuff
Hauptquelle
from?
aus den sogenannten
Cobalt is being talked
Vulkanvorkommen
about a lot
hauptsächlich
because
in
the main source is
Zentralafrika
coltan ore
Coltan
from
ist
Central
eine
Africa,
Zusammensetzung aus,
and
Polymer
coltan
und Tantalit.
is made of
Das
columbite
sind,
and tantalite,
Minerale, die
which are two
eng
minerals
verheiratet miteinander in
that
den
are
Lagerstätten
closely stuck
abgebaut
together
werden
in the
und
deposits,
die hauptsächlich eben in Zentralafrika vorkommen.
and they're mostly found in
Und,
Central Africa.
Kobaltit ist eine Quelle für das Element Niob.
And the cobalt is also a source for niob, and the tantalite is tantalum. And these together also bring some cobalt with them. Nature probably thought of something about that, maybe didn't, just dumping them on the same place, so we can all get them from the same place. So the discussion next is, where do we get all the lithium? That's mostly from South America and from China. Similar problem with the graphite. We need a certain quality of graphite for very high performance cells. Main producer, China. So the question is, do we really want to start an economic war with China if they can just say, yeah, so no more battery components, and so you're not going to be able to make any batteries and won't have any?
Mehr dazu kann man sich bei Methodisch Inkorrekt nachhören.
The podcast Methodisch Inkorrekt has something about this. I listen to a lot of podcasts, and you can imagine.
Möglicherweise hat der eine oder andere.
And some of you may or may not know the background about this. I can very much recommend, if you're only slightly interested in science, to listen to this podcast. It's very interesting, very fun, and you can learn a lot.
So then, what a battery needs is an electrolyte, which is the liquid between the both electrodes, because you need to have the ions inside something, because the metal won't just go from the one electrode to the other one. Therefore, there is the electrolyte. You use these carbonates, they are called. They have the property that they are very highly polar. And in addition to that, they are not acidic. Because there are also electrolytes which use their hydrogen atoms and give them away, so like with water. And if you put kali metals into water, then that's a really bad idea. So it means that there's a certain condition to the electrolyte. And this class, the carbonates, they provide that. And you can see they are hygroscopic, so they attract water, and this is the reason why you definitely should not open the batteries, because it will pull in the water, and but in the best case it would lose its ability to store energy. But in the worst case, it will get warm and you get fire. For example, another way of this is this way. So, how of you have put apart such a battery? Not that much of you. Maybe 20. I myself have disassembled a lot of batteries from laptops and stuff. There's always a small PCB in front of it, which takes care that the battery is not going too low in voltage or too high, because if you put in too much energy, then these metal spikes will be formed as whiskers, and they are thin and long structures for metal, which will grow at too high voltages, and then they are peeking through the cell, and you get a short in the battery, and you get this problem here. Has any of you had such a device? This is a Samsung Galaxy Note 7. I see one hand. Maybe there's a second. I think that's been for 1.5 and 2 years ago. Then these devices started just to burn from nothing. in parts in the pocket of its owner. What has been what can be seen here, that there is an X-ray image of the battery, and there are the electrodes, and the bigger part is the isolator, and at some of the batteries this isolator was too small, and through some hits from the side the foils were bending, and at one place just getting into contact with another one, and the battery had a short, so it got warm, it caught fire, and the result you can see in the picture. Not that good. So this is something which you don't get rid of with any energy storage. You need to get them safe. But also the weight is taking its role, and lithium polymer batteries are in that point very good because they are much lighter. So what's in current research are different materials for the electrolytes, where you get rid of the cobalt problem. There are plans which you probably heard in the media from Tesla, that nickel is going to be replaced, cobalt is being replaced with nickel, because it's very similar, they are very similar to each other, they're next by in the periodic system. Also nickel has problems which you probably know if you're allergic to it. So it's not without problems, but you have to look which problem is solvable and which you would just have to take in. Very interesting, you also could replace the cobalt oxide with silicon, which means that the same material you build your ICs from, the silicon, you could prepare it in a way so that you can use it for batteries, because it also has this grid structure, this hexagonal grid structure where the ions can fit in. In fact, the place is even a little bit bigger than the cobalt oxide, but this just works for once, because the silicon is integrating the lithium in itself. It gets physically bigger. When it's gonna be discharged again, then it gets smaller and cracks are forming. So you don't have a nice plate as an electrode, but you have some crumble. And this is one of the fields of current research, how to get this problem, how to solve this problem. So you could use silicon and get rid of the problem, how to discuss the things about cobalt and Africa, how is the ethical situation. With the electrolytes the same. Metal ions, there's an interesting story to the metal ions. In the 80s, when there has been the fundamental research to the batteries, then we thought about sodium as a metal for transferring the charge between the electrodes. No one knows something about this so right in the moment in the public press, but there's still research. These batteries are working quite well, but they need very high energy. At room temperature they don't work. It's probably something for trucks or for energy storage at some power plants. But at home or in your device, that's not an option. But in principle, it's pretty similar what you can use. And also sodium, there is plenty of. You have this in every ocean. You can just get the salt from the from the ocean and then use it. And you would get rid of the problems being dependent on China or South America.
Something about hydrogen, that's not that much my topic, so a little bit a higher level overview. This is a state diagram of hydrogen. Hydrogen is special. Which one of you knows from camping, for example, these gas burners you can run on cartridges or those big propane bottles? Yeah, 80-90% at least. Which one of you has accidentally opened the valve and then screwed off the hose? How many of you? Yeah, a few. Okay, different example. Which one of you has refilled a lighter? If you don't do it right, then there's a hissing noise and it gets cold. So in chemistry we call this the Joule-Thomson effect. If you remove the pressure from a liquid pressurized gas, so a pressurized container, you open the vent and the internal pressure drops down to atmospheric and it gets cold. With most gases it's that way. Not with hydrogen. Hydrogen gets hot. And that's bad when you have a leak in a hydrogen tank. You have to be careful about that. For example, in space travel, where you're filling rockets with the stuff, you have to watch out for this effect. There are 3 filled-in areas in this diagram. Number 1, to the left on the orange line, is the liquid storage of hydrogen. And you can see mainly if you look at the temperature axis at the top, we're at minus 260 degrees. There's not much room until you hit absolute zero. This is also called cryogenic hydrogen because you can't liquefy hydrogen above the temperature described by the orange line. If you make the hydrogen warmer, it'll still be under pressure and still be highly compressed and relatively dense, but it won't be liquid anymore. And if you heat it even more to hit the area number 2, you can see what happens at what pressure and what temperature. And you have about 500 bar in a pressurized gas bottle, like for welding. And those commercial bottles are usually 200 or 300 bar. This diagram goes up to 1000, which means that you have to do some convincing to compress hydrogen. And at the top, the area number 3 is the transcritical area. Critical point is the point above which the difference between the states of liquid, solid, and gaseous sort of melts together to one state where the different phases can't be differentiated anymore. This isn't actually liquid, not really gaseous, it's something in between, but you also need very low temperatures. That's one of the aspects that are not that good for using hydrogen as a fuel, because you have to to cool the stuff and keep it cool, and that needs a lot of energy and infrastructure and insulated vessels. If you poke a hole in one of them and it gets out, that's very problematic because of the Joule-Thomson effect, which heats the hydrogen up. And this also means that if you think about where hydrogen can work, well, as far as I see it, mostly in situations where you need large amounts of it at once, and known places where you have time to fill up. So the whole thing, I need 5 minutes to fill my diesel at the gas station, but I need 10 or 20 with hydrogen, and then the gas station has to sort of regenerate and cool down. You can do that, but for individual transport of person, it's completely useless. I'd say on a large scale, you simply can't do it due to dangers or whatever. But maybe buses, ships, possibly planes can be fueled by hydrogen, because they fly or move from a few known points. You don't have to put gas stations everywhere, but you have a certain points where you can keep the hydrogen and you can deal with it in a safe manner. With individual transit, yeah, you can do it. Some people are doing it. If it can be done at scale, I don't know if that's a good idea. But saying hydrogen is useless as a whole, or is too expensive, needs too much energy, or is dangerous, that's also wrong. You have to look at your use case, see what you can deal with, and then you can say, I'm using this medium of storage, or this one, or this one. With batteries, it's the other way around. You always have to carry the material around with you. You have the battery, the electrodes, cobalt oxide, graphite. It's always there. You have to carry it around. And the lithium ions just move from